So, Dr. Khedkar, how are you?
Good, good. How are you doing today, Bhavya?
I'm well. I'm well. Just to give an overview, I would like to talk to you about quantum hardware, its implications, and the entrepreneurial landscape majorly. Right? We can go on to talk about tangents and different things, but these are the prime subjects that I would want to talk to you about.
Yeah,
But
absolutely.
before anything else, I would like you to give a brief description about yourself, your work, your background, and yeah.
Sure, yeah. To start, I am currently a second year PhD student at Yale University. So I don't have my doctorate yet, but hopefully will in a few years. Um, I work in quantum information hardware. I work on quantum information hardware, specifically superconducting qubits and different ways that superconducting circuits and technology can be scaled up to hopefully, someday create a functioning quantum computer. That's sort of one goal, but being a research lab, our other goal is also just to do cool things with these circuits and see how much new physics we can explore. And so I've been working on that for a couple years now. I work with Professor Robert Scholkoff, who's been doing this sort of thing for about 20, 25 years or so. Um, and before that, I did a little bit of research in undergrad in a similar vein, and also worked at a startup whose goal was to more specifically think about the engineering challenges involved in scaling up these qubits into a larger computer. So definitely have been interested in quantum computing specifically for a few years now, and hopefully can continue doing this type of research and find a job in this field after graduation.
You know, talking about the different kind of qubit technology. What currently is the most efficient and effective qubit technology that we are working on?
So there are many different contenders right now, and I think we're at a point where it's unclear which hardware platform will be the one that reaches, a million qubits or 10 million qubits first, however much we need to sort of have a full scale, fault tolerant, general purpose quantum computer, as they call it. And right now, there are many different competing technologies. Superconducting circuits is just one aspect of the whole field out there. Many people have been working on using atoms as a basis for computing. They've been working on using ions. People do things with the different polarizations of photons, because fundamentally, what you sort of need for a logical qubit architecture is some physical phenomenon that can be manipulated in a way to have two different addressable states, and can be manipulated to create well-defined superpositions between those two states, as well as create entanglement between one qubit over here and another qubit over here. Because creating these sorts of large entangled states that are superpositions of many simultaneous qubits is sort of where the power of quantum computing comes from. And so there's many different factors to consider when trying to create a hardware platform that can do these things efficiently, right? You might think that gate speed is maybe the most important thing, right? Having a very fast computer. Um, but also, what really matters as well is how how well can you kind of protect your qubits from noise in the environment, right? These qubits are much more sensitive to single particles, dust particles, or thermal photons, and all these things that classical computers don't have to worry about as much. And so it's kind of still a race to figure out who has the best kind of trade-off between a fast enough computer as well as a noiseless enough computer. So the platform I work on, for example, has relatively fast gates relative to these sort of atoms, for example. But our noise our sorts of qubits are susceptible to a lot more noise than the atoms are. So there's all these trade-offs people have to think about, and we'll see in the next few years if anyone is able to kind of make very major breakthroughs in one discipline versus the other.
Uh, to to completely break down the entire process of building or formulating a quantum architecture, right? How would you, for somebody who's got absolutely no background or know-how about the quantum technology, how do you explain to them what goes into formulating or building an entire quantum framework or architecture from step zero?
It's a great question. I think, it always helps to put these things in the context of how classical computing architecture has historically worked, right? So what I work on in quantum is the hardware level, and in classical technology, that's sort of been figured out for a very long time, right? The fundamental way in which to create a bit. People recognize that you take a particular semiconductor, you make a uh, transistor like cell, and then you essentially keep scaling that up, right? And so at the logical single bit level, that's one thing to figure out, right? What is the hardware? Then the next thing is scalability, right? How do we make, the large equivalent of an integrated circuit, for example, right? And those two things are kind of sort of more the hardware layer. But, beyond that, it's how do you how do you get sort of this hardware to understand a more complex program in Python or something, right? There are these compile steps that you have to have where that turns into assembly language, and then the assembly language has a certain way that it runs on the hardware, right? So all these steps you can keep building up and up and up until you get to the classical algorithms, right? Which are essentially, math problems or word problems where you say, I want to do this particular task. What's the most efficient way for me to do it, right? And quantum computing has a very similar stack up, right? There's the hardware level, there's a compile step that you need to kind of interface between hardware and software. And then there's the quantum software, the quantum algorithms that get implemented in a specific way. And at the highest level, there's a way of thinking about, how do these quantum algorithms really work from a math perspective? And that is sort of what drove the initial interest in the field, right? Is that people figured out first, oh, there's all these cool quantum things that we can do if we were to have an actual quantum computer. Here are some crazy ways we can manipulate superposition and entanglement to solve many problems much more efficiently than they could ever be solved using any type of classical algorithm, right? And I should, clarify that solving something more efficiently and solving something faster aren't necessarily the same thing, right? The efficiency of an algorithm has more to do with how many steps does it take, right? How many logical steps does it take to go from point A to point B, from problem to solution? I think when we say that computers are getting faster every year, right? Or, a computer can multiply two big numbers today much faster than it could 50 years ago. That's not necessarily because the existing algorithmic implementation is any different, right? It's more a question of hardware has been made more efficient, and many things can work in parallel together that couldn't before. Um, and now it's faster. But the algorithm is fundamentally the same. And I think with quantum algorithms, they're fundamentally different. They might not be faster yet than classical computers because the actual gates to do the algorithm step by step are still slower, right, than a classical computer. But the dream is eventually, if we get those gates to be as fast as the classical computer, then the quantum algorithms will be genuinely faster and more efficient. And so that kind of, that layer of algorithmic complexity has been really, inspiring people for many, many years, but there are still a lot of problems to figure out in terms of this, this sort of stack up for quantum computers relative to classical, because how do you get kind of these quantum objects to give you information, right? Say you want to run some algorithm. How do you get them to give you information in a way that you can interpret, right? Fundamentally, all the information we receive back and we measure, that has to be classical information, right? And so when you're developing, um, a hardware framework, a compiling framework for thinking about how do I translate this algorithm into machine code, you need to have a way to process it on the quantum hardware, but then also interface that quantum hardware with some classical hardware, right? And then you have to think about these things like how do I do measurements super quickly, right? How do I collapse all this very complex quantum information into a few classical signals that give me as much information as possible, as quickly as possible, right? And so there are a lot of these sorts of interface problems to think about. I think one dimension that I also didn't really mention explicitly is this idea of quantum error correction, which sort of sits on top of, it's a little higher level than thinking about a physical qubit, but it has a lot to do with the specific way that you implement your hardware architecture. Because quantum computers and quantum bits are so much more susceptible to noise, They require a lot more. People in the field have to think a lot more about how to make sure they can preserve their information for as long as possible, right? You want to think of this idea of like a logical qubit, which is made of maybe many physical qubits. And even if physical qubits are susceptible to noise, then hopefully there are ways to engineer this where the logical qubit as a whole retains its information. That's something that you don't. There are sort of schemes to do this in classical error correction, but in terms of building a classical computer, people haven't had to worry about that as much, as my understanding. But that's actually quite a critical step to implement before anyone even gets to this whole concept of thinking about a compiler and interfacing with software, because you really, you need that information to be preserved until the point where you can do some measurements and remove some classical information from the system. So that's kind of sort of the outlook of all these steps. And, there are a lot of similarities to classical computing, but there's also a lot of differences, right? A lot more complicated problems to think about as well.
With how AI is permeating and bleeding through in pretty much each and every facet of research or work in general, how, as a researcher, how do you think that AI or the potential of machine learning algorithms, they contribute currently and potentially in the future they can contribute in the advancement and development of quantum technology?
Yeah, I think there is an interesting relationship that this field has with AI, which is, um, ML problems are fundamentally some kind of optimization, right? And classical computers, the efficiency with which classical computers can solve um, a lot of these optimizations is kind of limited by the computational power of a single computer, given how many kind of parameters need to be optimized, right? To sort of be taken into account. And that's why a lot of the development that's happening with AI today is only really being made possible by the hardware catching up with all of these ideas, right? That's kind of a nice parallel, right, to quantum computing, because similar to quantum computing, a lot of these ideas, the idea of doing like a support vector machine and all these other things, have been around for like decades and decades. It's just that no one had this scale of hardware that we have today, right, to implement them in a useful and kind of demonstrative way. Um, I think that as far as AI's role in the development of this technology, one thing is that there is a specific branch of quantum algorithmic research that is called quantum machine learning, which has a lot to do with how quantum computers can be leveraged in a way to solve a lot of these problems that AI is attempting to solve with similar models. And it's interesting because there's from my understanding, and this is not really my area of expertise, but from my understanding, there are certain ways to model problems in AI that lend themselves to be naturally implemented on a quantum machine. Um, there's all these, a lot of problems in AI generically can kind of be described as finding some kind of global minimum of some very complex function, right? And it's very difficult for a classical computer to understand how to find a global minimum as opposed to a local minimum, and these computers can often get stuck in suboptimal solutions, right? Versus if you implement things a very specific way on a quantum computer, due to these properties that quantum objects have, where they're able to tunnel or kind of explore many states, solutions in a very large state space at once, right? They can actually be shown to more reliably find global minima of very complex functions. And so, if you adhere to these types of models, then once quantum computers become fast enough or big enough, like it makes a lot more sense to start using those to solve some of these problems. That being said, I think one thing about quantum algorithms that maybe not everybody's aware of is that uh, quantum algorithms are very good at solving very specific types of problems that are implemented in very specific types of ways, right? If they don't fit the math model, uh, if your problem that you want to solve doesn't fit a math model that quantum computers are intuitively better at, then there's no reason to believe that they're going to be any better at solving anything than a classical computer is, right? And so, now because there's so much interest in quantum computing, people every day are coming up with more and more ways to map problems in classical machine learning onto quantum machine learning, and tweak all their math models and figure out what can be done and what can't be done. So it's a very active area of research, um, which will hopefully be pretty interesting. I mean, obviously AI is something that a lot of people, a lot of benefits to be had, right? Like a lot of very blatantly applicable ways in which to use this technology, right? And so I think this sort of branch of quantum computing is definitely going to be from a very large focus for people for some time now.
If you had to state a timeline for in regard to the advancements in the domain of quantum mechanics and quantum computing, or in general quantum technology, how do you see the potential of probably quantum communication, quantum networks, and in general, like the probability of internet being probably substituted by quantum networking channels, because we know that quantum algorithms and in general the sheer potential of quantum information and technology, they make susceptible our current cryptographic mechanisms and frameworks, as well as the current internet and the online infrastructure. So two primary questions. First, how long do you see that such a reality could materialize? Secondly, what are the ethical implications, and how do you see that future researchers and people interested in the field can tackle these challenges?
Yeah, I think the timeline for really being able, I think, the thing that people talk most about is Shor's algorithm with regards to any kind of cybersecurity adjacent applications of quantum computing, which is that there is this algorithm that can only really be implemented on a quantum computer that can has been proven to be able to crack a specific type of encryption known as RSA encryption, which is the backbone of a lot of cybersecurity infrastructure on the internet today. And it can do this in an efficient way. You know, it can do it much, much faster than any classical computer would be able to do it. The whole premise of RSA and the premise of cybersecurity encryption methods writ large is that it's not that breaking the encryption is physically impossible. It just takes an unfeasible amount of time, right? It requires kind of searching for a solution that definitely exists, but would just be way too impractical to attempt to actually find. And so there has been a lot of talk about this, right? Like this algorithm has been around for 30 years now. It was invented in the mid 90s by Peter Shor, long before anybody had any, semblance of quantum hardware, or at least, the idea of networking many quantum bits together. So the idea has been around for a while, but that being said, I think the scale at which RSA deals, the input size of the problems are these massive, massive numbers. And in order to kind of formulate this problem and extract a solution on a quantum computer, we would need way, way more qubits than anything we're capable of right now. Millions, millions, tens of millions. We are a long ways away, I think, from that goal. I think, obviously there's been a very favorable scaling of qubit technology in recent years. 10 years ago, there were no companies that had more than, a few bits. IBM at that time maybe had like 100, I think. I'm not even, yeah, it's been a long time since, the early days, I guess. But now, there are companies whose qubit count is really doubling every year. IBM and Google and some other places have demonstrated that they can control over 1,000 qubits. And so, people might say, okay, well, if we went from 1 qubit to 1,000 qubits in the last 10, 15 years, there's no reason to believe that we can't get to 1 million qubits, in 10 to 15 years if we follow this sort of exponential scaling. But I personally don't really think that's true. I mean, I'd love to be proven wrong as well, but I do think that like making 1 million qubits is a very different challenge from making 1,000 qubits. And there's a lot more engineering challenges you have to consider, not just making them physically, right? but rather having the sort of connectivity between all 1 million of those qubits that would actually the sort of connectivity that is required in order to break something like RSA. So I think that is like at least a decade away. I don't really think that that's happening anytime soon. I think that with regards to the quantum internet, I think that's an expression that gets thrown around, and I think people anticipate that our entire internet infrastructure will be replaced by some new infrastructure. That is definitely, I don't think that's on the table. I think that our existing classical internet infrastructure is excellent for 99.5% of the vast majority of anything anyone wants to do, right? Communication is already pretty much as fast as it can be. The hardware is already there. There's a whole kind of all these existing protocols exist, right, that can really only be implemented very well with classical technology. And for most of us, for anything that we want to do, the internet works totally fine, right? Um, I think that there are just a few different people and different organizations that would be extremely interested in having, extremely secure communication. I think that looks more like, the U.S. military, for example, right, is one of the biggest investors in quantum computers for exactly this reason, because they're interested in kind of having extremely, extremely secure channels of communication, say from two different points in the country, that are very well protected against hacking. And there's all these quantum methods of doing encryption that are very, very different from RSA. And so, maybe people like them will kind of invest in the hardware and the research in order to get to that point. But I don't think for the rest of us, I don't think that that's really a thing that we're going to end up using. Um, it is an interesting question to think about, though. If someone is able to intercept classically encrypted information, like when you buy something on Amazon, send credit card information across the internet, right? That's all RSA encrypted, and so maybe there will be people that are capable of intercepting that information and employing some kind of quantum hacking method to do something with it. It is an interesting question. I don't um, I don't necessarily see the whole infrastructure changing though as a result of that. I think that's quite a lot of work, but it'll be interesting. It'll be interesting to see.
You briefly touched upon a facet that I wasn't really going to talk about, but it suddenly clicked to me. Uh, every novel scientific endeavor has been to an extent capitalized upon to do good, as well as used to probably to just weaponize its essence,
Hmm.
maybe
Hmm.
nuclear technology or currently artificial intelligence and the autonomous forte. uh, it's far-fetched and there's a lot of time to it, but what are the potential ways that quantum technology might be weaponized, and how do you think, what are the ways in which nations can safeguard against implications of such a potent technology being weaponized?
Yeah, that's a great question, and it reminds me that I sort of forgot to answer your second part of the previous question about ethics, but maybe I'll lump this in together with that. I think that is definitely something that people are not thinking enough about. I think from a scientific perspective, it's very exciting that there exists something like Shor's algorithm, because it's just cool to think that there's a way to solve this problem that was previously considered to be, intractable in any reasonable amount of time. And I think that I think that it's important, when you're in research and you're developing these systems and you're getting funding from all these external sources, right? It's important to take a step back and really think, how is the technology that I'm going to develop, how is it going to be used in the world, right? If you're being funded by someone like the Department of Defense, for example, you should just be aware, these are kind of the goals of an organization like the Department of Defense. They relatively clearly they sort of outline, the reasons for giving out the funding that they give out and the types of technologies that they hope to develop, right? And I think, wherever you stand, like politically or, on all these different things, I think it's important to understand your funding sources like that, right? And understand what people intend to do because as a pure, as a pure researcher, you're developing something and then someone is going to take that and they're going to do something with it, right? And you have next to no control, right, over how these things get used. So I think one really important thing in terms of like the large scale is that it's important for scientists in the field to work with policymakers and governments and really kind of communicate advantages, disadvantages, expectations, make these things very clear, right? I don't know if you saw, I'm sure, a lot of people have seen Oppenheimer, but I think, that's an example of where scientists and policymakers, maybe some people were trying harder than others to be on the same page, but a lot of, really terrible things happened because, you know, uh, scientists kind of underestimated what people were interested in doing with the technology that they were developing, right? And I think nowadays more and more people are kind of on these things like White House advisory boards for quantum information, for ethical science, for climate science, right? Like any type of technology, right? These are the important things to consider. How will they fit into policy? How do we start to make policy now that kind of has, preemptive measures or preventative measures to make sure things don't spiral out of control, right? Um, my professor is on one such committee at the White House, and he goes there pretty often and has this kind of science communication relationship, which I think is extremely important. Um, I'm not sure what that looks like, what the equivalent would be in other countries, but I would hope that any country with significant research in this field wants to cultivate that kind of relationship with the policymakers, because those are also the people that will kind of in addition to making rules, a lot of politicians are the ones who communicate things to the general public, right? I don't think scientists are necessarily the best people at doing that, really. Maybe a select few are, but most of them are kind of out of the public eye, right? Um, and Biden, for example, he's interested in quantum technology, and during his presidency, he has released some statements and is showing initiative at trying to understand what it does. And I think as the government learns, so too does the public learn along with them, and kind of spreading awareness at the stage is very important, right? I think we've seen kind of what happens with something like artificial intelligence when everybody gets very excited and they kind of run away with something, right? Or gene editing, for example, like from the very early days of the technology, it's important that expectations between people are clear. I hope that answers your question.
It does. It does. Rather fabulously, actually. Uh, I'd like to pull a complete 180 from this practical and pragmatic discussion that we are having, and I'd like to take a philosophical tangent. And how do you think the understanding of quantum mechanics also aids us at understanding the essence of consciousness and existence?
Yeah, it's a very interesting question, and I should preface this also by saying that there are some very qualified people out there working on this. I'm not one of those people in terms of, really thinking about it, but, naturally when you study quantum mechanics, you start to wonder about these things, right? I think this whole idea of determinism, right, is challenged, right? Because quantum mechanics really suggests that there is no such thing in some cases as a well-defined outcome, right? Um, and if an electron, doesn't need to decide what state it's in until the point of measurement, right? Then what is the reason to believe that some aspects of the human brain or some aspects of the rest of the world shouldn't work in a similar way, right? The fundamental philosophy has to do with do things exist independently of whether we can observe them, right? Um, and so there are some people, I think, thinking about the ways in which these very complex patterns in the brain are, can be modeled as quantum, quantum states, right? And they collapse in a certain way when it's time for us to make a decision, right? I think, that sort of means that our brain is hiding a lot more computational complexity than we even realize, right? And even the idea of studying something like that is so strange. I think that's the other thing that quantum mechanics has taught us over the last 100 years, is that like you kind of have to throw out all your intuition if you want to, go into something with zero assumptions and really, really try to understand. Um, and I think, when you think about these things, I don't think you can let it keep you up at night too much. You still have to live the rest of your life the same way that you would have lived it. Um, but it really makes you appreciate things, right? Like it really makes you kind of see see real beauty in this idea that even though things are maybe a little bit undecidable on a small enough level, when you get to the scale that we exist at, everything kind of works out, right? Like it's nice that all these theories kind of converge together, and it's very fascinating to study stuff at the boundary. um, but it's nice to know, my kind of personal belief is that maybe this is more of like a spiritual take rather than a scientific take, but I think that any scale at which we're making decisions and doing things, I think there's always some aspect of determinism. Like we're all still responsible for our actions. We're all still, or rather, I should say, like there's I shouldn't say determinism. I should say there's some trade-off between free will and determinism, right? Some things are beyond our control, but we are responsible for certain things, and we shouldn't live at one extreme or the other extreme. Um, I don't think we have to behave the same way as electrons do necessarily.
In continuation to the same deliberation that we are having, the world of sci-fi and pop culture is abysmally intrigued by the concept or the idea of temporal manipulation, things like time travel and the concept of multiverse probably. But if you look at these things from a lens of current pragmatic science, how does how does real world science explain these phenomena or these concepts or notions?
Yeah, I think there is a lot of sensationalism, which is fun, but it's important to know that, I always say this to people. I say if someone had invented time travel, into the past at least, then they would have shown up by now. You know what I mean? Um, and I think that concepts like that are really interesting to think about, but there is really no physical basis for understanding them at all. I don't think anything about quantum mechanics really kind of explains that sort of thing. There are different senses in which, time. I think this is something that is explained a little bit better by something like relativity, which is kind of on the opposite end of the spectrum, right? I think relativity has more to do with very large things, right? Very, very, very high amounts of force and energy and these things that happen at the other boundary of physics compared to what we study, right? And there is, of course, scientifically verified evidence for the theory of relativity, which says that time can pass differently for two people depending on how fast person A is going relative to person B, or the sort of gravitational field that person A finds themselves in. Right? You can actually do all these things like interstellar, where you go to some planet that has a lot more gravity, and then you come back and everybody's much older than you. Right? I guess I think that's the most realistic way of time traveling into the future. I don't know if we're actually going to do any kind of time traveling that involves getting into a machine and then like showing up somewhere else. And there's ideas of teleporting around the universe and wormholes to all these other things. And I think, again, it's a question of A, like what actually exists, and B, are we ever actually going to be capable of studying this information, right? Um, is it ever really possible for us to even know what happens inside of a black hole, given that the only way that we measure things is through light? For the most part, that's the only way that we know how to interact with things, right? Light and gravity to a certain extent. But if, a black hole kind of absorbs any light, and it, doesn't allow us to do that, and no humans can go into these things because everybody will die. Like, so I don't really I don't really know if there's a feasible way to study all these phenomena, but that's probably what people said about quantum mechanics 200 years ago. So I shouldn't make any assumptions. Um, but I think it's great to have this kind of high level interest in science in the public, in the community. Like, I think it's really cool. I think these days, at least a noticeable difference from my sort of childhood, is that it's cool to think about these things now, right? It's cool to think about the prospects of something like time travel, or Ant-Man going into the quantum realm, or like I think people should be excited about having interest in these things, and they shouldn't necessarily be like um, they shouldn't necessarily feel like they have to like hold those interests inside of themselves. It's nice for people to share these things with each other. So I think it's all great. I just don't think we should be taking anything too seriously that we see in any of these movies.
You know, agreed, 100%. I mean, from a perspective of, if it is a factor in fueling your passion towards the subject, well and good. But if it starts to overtake the realm of possibility with regard to our current understanding and technology, well, it's quite far fetched to see it that way. But again, now, taking a little turn towards the matter of the entrepreneurial angle or the entrepreneurial landscape with regard to the quantum domain. You've worked in the academic space, and you still are, and you've also had the experience of working at the in a technical environment, in a startup, in a quantum startup. How do you feel the what do you feel is the difference, firstly, between the two environments, and what is the a significant difference between the objective between the two workforces?
It's a great question. That is definitely something that I have spent the last few years thinking about. I think it was a pretty big decision for me to decide to work at a startup after graduation, as opposed to going straight to graduate school, which is what I think most people that I'm around, they kind of went straight in after undergrad. And so, there were certain things that I wanted to understand about the research startup environment. Um, I think for quantum computing, things look a little bit different when you compare startups to academia compared to other fields like computer science, right? Computer science as a discipline is so mature and widespread in its education and its feasibility to implement on your own, right? Anybody with a PC can download the latest version of Python and start doing something. The quantum space is very, very different, right? It is so early stage that every startup is in some sense also concerned with some pretty fundamental research, right? Because, it's, like I said, no one has really figured out the hardware yet. A lot of things about software also need to be figured out, and error correction and all these things, right? So the average quantum computing startup is much more academic in nature relative to what startups look like in other disciplines. And that's something that I really liked, because I think if you want to express creativity and find creative solutions to problems, um, especially problems that are sort of, a little bit academic in nature, right? Then it's cool to be in an environment like that, right? Where you're still doing research, but the kind of structure of how things work is a little bit different. So I'll explain that. Um, when you research in an academic lab, right, you're maybe concerned with a very small scale of things for what we do, right? For hardware, for example. I'm thinking about how to create interactions between a couple individual qubits, right? And trying to create new types of interactions, right? The way that I do this operation is different from the way that people have done it before, right? And research is all about tangents in an academic setting. You're trying to solve some problem, then you find something interesting, and then you say, oh, let me just take a break and let me go down this interesting rabbit hole and see if it leads somewhere, right? The mentality that you have to have in academic research is a bit more like that. It's a little bit more exploratory. Versus in a startup, even though you are doing research and you're trying to come up with good ways to do operations and, kind of demonstrate things on an individual level, you also don't really have time to think about that a little too much, right? You need to also kind of say, okay, what we have right here is good enough. Now let's figure out how to make it bigger. And there's all these other challenges involved in making things bigger, right? How do we get connectivity between 10 different qubits? That's something that you don't really think about in like a university lab, right? Because it involves so much more hardware, so much more people power, right, to put these things together, to measure them. Like it's a whole production, right? And so those are very interesting problems to solve too. But the nature of how you solve them in a startup is you're one of many. You're on a team. You have a specific role on a team, right? You're all working together to achieve some common goal. It's a really nice support network, right? Because a lot of people, especially post a PhD, they have many different skills, and you can go to other people for help on something, and vice versa. And as a collective, you get things done much more quickly, right? I think in an academic research setting, those are kind of not necessarily the priorities, right? The groups are honestly much smaller. In hardware, maybe there's two or three people working on the same project. In software, in theory, maybe it's just one person kind of doing everything by themselves, right? And the reason that it's like that is because research in an academic setting is meant to be challenging, right? The goal is not to have some finished product, but the goal is to approach everything with the mindset of you are going to learn something, right? Like you are really going to struggle through something. And when you get to the end of that struggle, you're going to understand it better than anybody else on the planet, right? Which is also a very cool thing. And so you sort of have to have this mindset in more academic research, which is something I'm finding now that's more like, okay, I'm trying to solve a problem. I don't necessarily know how to do this, but rather than going to someone else on my team for the sake of the project and being like, hey, can you show me how to do this so we can get everything done faster? The mentality is more like, you know what, I'm going to sit here from the ground up. I'm going to figure out how to do this. If I really, really need help, there's always people around me that I can ask, right? But my project is my project. Or like if I'm working with someone else, it's like, I have my responsibilities, my partner has their responsibilities, and I need to figure this out for myself. And it's very difficult in the beginning. Like I found it to be definitely, I think the last year or so of grad school has definitely been, on the one hand, like the most challenging year of my life, right, intellectually. But at the same time, the flip side of that is it's been sort of the most educational and informative and inspiring year of my life. I think that you really you have to channel that kind of struggle into something positive and come out of the other end really feeling like you've gained a lot from the experience. And I think that's one of the most rewarding feelings that there is. Um, but startups are great too, and could be a great environment. After doing a PhD, you decide, okay, I don't want to try to do everything by myself all the time. I want to be part of a team. There's certain things I like to do and certain things I don't like to do. I want to specialize in, maybe you only want to run simulations or you only want to do math. There's always a place for you at in a startup environment like that, which I think is great too. And it really depends on where you are in life.
Another aspect that I would like for you to talk about is the difference between the flow of investment and capital between startup and a research endeavor. Like
Yeah, that's a great question.
what is the dynamic there?
Yeah, so the avenues tend to be a little bit different, actually. The way that investment in quantum hardware at least works, and software as well, is there are a lot of government grants. So, like I mentioned earlier, Department of Defense, for example, right? Or National Science Foundation will sponsor people to do research. Um, there are kind of these more like public sector avenues that have money that tend to finance projects. Whereas with startups, it tends to be, the success of a startup, and this is kind of a thing that is true across other disciplines as well, from my understanding, is you really need people to finance you who have a lot of money to spend and, are investing very early stage and are going to see the whole thing out on a very personal level. And so that tends to be these like venture capital firms, right? These firms with a lot of money that specialize in understanding a certain type of technology. And, every year they hedge their bets on many different tech companies, for example, and they say, okay, let's put some more money in this one, or let's not give some more money to this one. And like, there's people from those companies that kind of interface with the startups on an individual level, right? And, once every quarter or so, provide updates to each other, and there's a lot of communication. That's kind of the major funding source for a lot of quantum computing startups, at least in the United States. I'm not totally sure about, again, other parts of the world, but um, that looks pretty different. And as a result of the funding source being different, um, the timelines are also very different, right, to deliver things. So at a startup, life is very fast paced. You tell your investor that you're going to do something in a quarter, which is 3 months, right? And by the end of the quarter, hopefully you've done that thing, right? And in a research startup environment, this can be especially difficult, right? Because now you're trying to do something where it isn't just a question of like, can I work hard enough to get this done in time? But it's also a question of like, will this even work? Like I'm doing something kind of new, like I have to meet a certain milestone and like I'm not even 100% sure going into it that this is like a feasible thing to be done, even if I had more time, and that can be challenging, right? But it teaches you to set realistic shorter term goals for yourself, I think, and gives you an understanding of like how fast is the right amount of fast to be working, right? You don't want to try to solve every problem at the same time. You don't want to try to do things super quickly and sloppily, but at the same time, you don't want to lag behind people, especially not behind your competitors, right? When you're a startup and you're trying to demonstrate why your technology is better than another startup, versus in an academic environment, you have these grants from the government. They have to be renewed every year or so, but you can make all kinds of different progress in different ways, and like at a high level, as long as you're kind of working on the same thing, you'll get these renewals, and it's a little bit more hands off that process, right? And so that's nice too, because you don't have to be worried all the time, like, oh, I have to do this thing in a few months and it's not working. Um, but it's important to stay motivated during a process like that, right? You have a whole year and you're like, okay, well, I need to do all these things, but I have a whole year, I'll get it done. But you need to kind of get it in your head, like, no, every day I wake up, every day I have to treat this like it's the most important thing I have to be doing, and I have to really teach myself how to make progress, even when no one is, wondering how things are going all the time, right? Which I think is a larger lesson about grad school in general, right? The kind of self-management aspect. So I think there are pros and cons to both of them, but I think because of the nature of the work and the pace of the work and what each institution there is trying to achieve, I think it makes sense to me that the funding sources, the nature of the funding is a little bit different.
Another aspect is that in regard to a business in the forte of quantum technologies, there isn't a particular set product that you can sort of capitalize upon by selling it to hundreds of people. The customer segment in general demands research findings and research insights, as opposed to a single product that you can sell and uh, build capital off of. But that's
Yeah,
again,
and the idea, sorry to interrupt, but I
yeah.
just wanted to add that the idea is that eventually we will get to that finished product, right? That eventually there is some quantum
Mm,
computer
mm.
that can be sold to a customer for X amount of money, and then you can provide software support. But the idea is that that customer can go for it and use that computer for whatever it is that they want to use it for. And so that's kind of, it's a good question. What is the end goal of a lot of startups, right? Because two things happen to startups, right? Either they turn into some super big company, right? Or they and they go public, or they get acquired by an existing big company, right? And so a lot of startups have to decide, like, what is the thing that we're trying to achieve? Are we trying to build a quantum computer ourselves and really, really make it bigger than whatever Google has right now, whatever IBM has right now? Which is a difficult thing to catch up to, right? Like, not only have those people been working on it for 10, 15 years, but they also have more people, they have more money, those people have job security, they're going to stay there, right? You have to have a lot of faith that your startup can catch up to something like that. Versus, if you get acquired, the idea behind that is like, we've demonstrated kind of something very good about our architecture. We're not necessarily interested in being the people ourselves to turn this into a massive thing, but we will help someone else with the existing tools and services, realize that kind of goal together. Um, and so really depending on kind of what you're going for kind of shapes how you think about how are you as a startup going to interface with clients and with customers, and like what are you trying to get out of this very this kind of the stage that we're in where you don't have a finished computer, but maybe in order to kind of advertise the benefits of your technology, you have a few qubits together and you say anyone can use our qubits and do some open source thing and do some measurements remotely and like things like that. There are things that you can come up with now that allow you to interact with customers and with clients and to kind of get more visibility, right? And that all goes into this larger goal of demonstrating that your technology is the right technology.
in, in the same breath, for somebody who's just looking forward to probably beginning a startup in the quantum field, what are the specific market gaps or the explicit segment demands that people can probably uh, work towards or work into delivering?
I see, like gaps in the existing market. That's a
Yes.
good question. I think there aren't a lot of people who are necessarily thinking about once there is a large, error correctable quantum computer, um, thinking about things like uh, things that are equivalent to a lot of classical technology. So, for example, like random access memory is something that is a very important feature of a classical a classical computer, right? Something that interfaces with the CPU to temporarily store information, so that the rest of the processor can go back to actually processing things, right? And can interface very quickly um, back and forth. I think that technologies like that now people are starting to think of them and think about how they can make quantum specific versions of those things that are more efficient than just like trying to do the same thing as whatever the classical thing was doing, right? Things like that. I would encourage people to think about sort of like the layer that's between the hardware and the software step. Getting more into the compilability of things and thinking about the software architecture meeting the hardware architecture. I think that's really important. I would also encourage people to. Um, I think one of the greatest things about this field and the way that these computers work is that they can very efficiently solve problems that can be modeled in a certain type of way. And for a long time, people thought those problems were specific to quantum mechanics or specific to chemistry or biology, like things with physical particles, right? You have these models with two things interacting, and you're like, okay, it has to be some particles, and these are the types of problems that we're going to solve. But, in the last 20 years, now that this technology has risen in prominence, every day, people are figuring out, oh, actually, there's this problem in the transportation sector that we've been trying to solve. And it turns out that it can, the trains interact in the same way as the particles, and we can map things back and forth. And if we can write the problem down, the problem that we want to solve in a totally different industry, if we can write it in a similar way, then we can get this quantum computer to do something that maybe we weren't able to do before, right? And so now there's this whole challenge of how do we take problems that we can describe in words and how do we stuff that into a model that we know that we can make some progress with, right? I think transportation, for the example that I gave, is a super, super interesting aspect of this. It's one that I personally would be interested in thinking a little bit more about after graduation. People have done a very similar thing for drug discovery. Now every few months someone puts a paper out there that says, here are some new things we've realized we can do with discovering drugs based on the models that are available to us through these quantum computers. Things with environmental simulations of hurricanes, I've heard that there's applications for that. So I would really encourage people, to kind of figure out what is important and what is useful and start mapping those things onto quantum computers, because that can only ever generate more excitement, more investment, more research, right? If we find out every day that more and more things that trouble people can really be helped out by this technology, I think that's the whole reason to do it in the first place. So I would encourage that.
We've been talking about research in particular quite a lot in this conversation. And I personally am of the opinion that research and writing, I mean, communication is important, but writing as a particular niche facet of communication clubbed with research is the single most impeccable skill one can harness and develop to garner success in pretty much each and every facet of life. So, like, my
Yes.
question to you is, how does one become proficient, efficient, and straight up brilliant at conducting research, curating results, and writing?
That's a question that I'm still trying to answer and figure out for myself. I think the research process is so fascinating. You have to be so meticulous, and when you make a claim, simple sentence, you say, "Oh, this thing that I've come up with is better at doing X application," right? That single sentence that sounds so simple on the surface level has to be thoroughly, thoroughly vetted. You have to go out there, you have to do your due diligence and make sure, okay, how many people have tried to do this before? What are the pros and cons of their approaches? What does my approach do better? Let's be honest about what my approach does worse. Why would somebody actually want to use my thing over somebody else's, right? And through grad school, I think it's a great environment where you really understand that, because anytime you make a claim, to your professor or to someone that you're working with, they're going to ask, okay, well, how does it compare to this thing? Why wouldn't you just do this thing this way, right? And all these little, feedback mechanisms or criticisms make you much stronger. And they turn you into someone that is going to really thoroughly investigate problems. That's kind of the best high level description I have of, really staying true to the research process. I guess I could also say things like, don't give up, but also know when the right time is to give up, because you kind of hit a dead end, and maybe it's something is not as promising as you thought, and it can be painful to part with an idea that you've been fascinated by. But you also have to recognize, if you've done as much as you can and things aren't working, you have to recognize when it's time to change course. And most of the great discoveries, of science in general have rarely been things that people set out to solve a very specific problem, then they actually solved that exactly the way that they thought that they would, right? Most things happen because people notice something and they're like, I recognize that it's time to go down a different path. So that's kind of what I would say about research, but I'm nowhere near an expert on any of that. I'm definitely still trying to figure that out. And as far as writing goes, I think that there's a few different types of writing. There's like extremely scientific writing, right? Which also has to kind of be well thought out, well cited, explained for the technical experts in a way that an expert can pick it up, just read your paper and understand exactly what you're doing, right? That's one thing. And I think another thing that is really important is this whole science communication aspect. I mentioned that I thought that scientists communicating with policymakers directly is super important, but I also think, scientists coming up with avenues to interact more with the general public and having more of an interest in interacting with the general public, or, people that they know, people maybe in their social media circles, I think that is super important. I think being able to condense down simple ideas, or sorry, complex ideas into a very simple, um, in a simple way that doesn't oversimplify things, right? It's important to be able to walk away from that kind of thing with a really good understanding of the important claims. Doing that is a skill that not a lot of people necessarily have. There are people that are brilliant at scientific, very thorough technical writing, but when it comes time to explain things, at a level that is, that they haven't kind of been used to being at in a long time, I think it can be difficult for some people to do that, right? And there's a lot of, actually Twitter um, is an important space for all this quantum discourse. A lot of professors and a lot of, experts are kind of on that platform, and every so often something interesting happens. They'll post a link to a paper. They'll give a very shorthand description of why it's important and what it's talking about, and that goes a long way, right? Especially for people like me who know, know a little bit, but might not really be able to understand the technical paper as well as I would like, right? And having professors that are really experts but also really good communicators break those sorts of things down, or even grad students. I know grad students that have started to do this sort of thing as well, and I think that's great. I think that kind of communication is very important.
There's this thing that gets thrown around a lot and is a very recognizable verbatim or statement is finding your own voice. I think what you just said is exactly regarding that. Like, that is what finding your own voice is. How you are
Yeah,
able to sort
absolutely.
of by yourself fathom a complex idea and then probably explain it to somebody who's got no context or background about it without taking away its essence and meaning by
Yeah,
oversimplifying it. So that is something that, again, completely agreed. The scientific community, the people at the vanguard of their scientific fields, they have to really garner this skill.
absolutely. And I think that, it's very important for young scientists and anyone that's interested in science, especially, at the college level or high school level, to invest some time into really taking writing seriously. Even writing in other disciplines, learning how to communicate your ideas, taking some, whether it's literature classes, whether it's some other type of humanities class, kind of honing out your skill set in that way, I think ends up being very important. I think some of the best scientific communicators that I know are people that studied many different things in college or beyond college and had many interests. Right? They like to read books, they like to read the newspaper, they like to do crosswords. Those people end up being the ones that are most articulate and kind of the best at interfacing between many different types of people. And I think depending on what your role wants to be, it's important to have those skills. If you're someone that definitely wants to do research forever and only write technical papers and you're fine with that, then maybe you don't necessarily need those other skills. That's a decision you have to make for yourself. But if you're someone that wants to be involved in communication, or anyone working at a company, really, right, at a kind of any kind of technical but also hybridized with some more management, or thinking about the long term, or communicating to higher ups, or communicating to people outside the company, these are all skills that you absolutely need for that. I think that's very important, and I don't think there's enough of an emphasis placed on those skills in the scientific community in general compared to some other disciplines.
If you have to lay down a roadmap for somebody who's not at all versed with the world of quantum computing or quantum mechanics in general, what would you recommend them? What approach would you recommend them to start with it and become fluent in the language of quantum mechanics?
Yeah, that's great. And I think the first thing that I'll say is, studying quantum computing and being a part of this whole discipline and understanding quantum mechanics, they don't necessarily have to go hand in hand, right? It really depends on what you want to do. So, as quantum computing evolves, there are more and more educational resources that are coming out where, if you want to get involved in quantum programming at the software level, you can read a textbook where the highest level of things is all that you really need to know, right? Like, you need to know there's something called a superposition, there's something called entanglement. These are the tools in my toolbox. Here are all the things I can do. It requires a good understanding of math, for example, but it doesn't really require you to get deep down into the physics, which is great, right? Like, I think specialization is what makes the world go round. And I think that if you're someone that doesn't necessarily want to do the physics, or, maybe you're a bit younger and haven't gotten the opportunity to study that physics in depth, you can still start to learn and to contribute to this whole field, and educate yourself. I would say that the way that which you approach education really depends on your where you are in life. I think, for example, I'll start with maybe talking about high school students and college students. There's a lot of resources being put into quantum education, even, at the high school level these days. Some schools are starting to teach it, or some kids have some clubs. And I think it's really great that people are interested. And I think that, if you want to do the computer science side of things, or like quantum hackathons and stuff, and if you have the requisite math background, you can start to get into that. I would also encourage people, though, to not kind of jump the gun and go into quantum computing too quickly. It obviously sounds very exciting, right? But especially, if you are interested in getting more involved with the physics, I find that it is really, really important and really helpful to have a strong, strong foundation in existing classical physics, right? And having a few years where you're learning things that are very conventional and have been around for a long time, really honing those physics skills, math skills, engineering skills. And so by the time you start really studying quantum computing, if you're interested in the research, you can kind of appreciate differences and similarities, and you develop a much more well-rounded understanding of the material. I think, for me, I didn't even learn physics formally until junior year of high school, my third year of high school. And I think that if someone had tried to teach me quantum computing in any aspect at that level, I think it would have been very difficult for me to understand, because so much about what you appreciate about it has to do with how it contrasts from what your expectations lead you to believe, right? So many times in science, we're faced with things when we're looking at our screens and getting results from our devices, and we're thinking, okay, what would I expect if this was a classical electron? And how is this different from the way this electron is behaving now, right? You can't make those comparisons if you haven't studied the original thing for long enough. So I would encourage people to really take their time, especially if you're a high school student or early college student. There's so much time that you have to end up getting involved. Don't be afraid to really have patience, really go slowly, and take things as they come as well, right? It's important to be excited, of course, but you should also, you should recognize that there's a reason that things are taught in a certain order at a certain pace, and like you'll be very grateful, right, if you take that approach a few years down the road, because you'll feel like you really have a very holistic understanding of what's going on.
As my final question to you, what is your message or advice for the up and coming people who are going to pursue or will be in the future at the forefront of the quantum domain, or in general the scientific domain in general?
I think, I think that hype is exciting, but skepticism is very important. It's one thing I would say. I think don't trust everything you read on the internet. Sometimes you'll see some article about how quantum computing is going to solve this or that, and unless it's some, very thoroughly reviewed paper, and it rarely is kind of a super publicity adjacent article, going to temper your expectations, right? Most of the time, it's going to start saying, "Oh, and this paper means we can do this and this and this," and having the kind of literary understanding and wherewithal and know-how to know how to navigate those types of articles or that type of discourse, with the right amount of expectations is very important, right? Because if you set the bar too high and you don't meet the bar, it'll all feel like a disappointment, right? But nothing's a disappointment here, right? We're doing things for the very first time. We have to take it slow. We have to do it right. Frustration in this field is a big thing, right? Especially when it's so intertwined with research. It's important to take that frustration inside, and channel it into some more productivity, right? Some inspiration. Remember that what you're doing is very, very cool. And cool things are rarely easy, and rarely can they be done quickly, right? And so that's the sort of trade-off that you have to be comfortable making in your head. Um, and I think the other thing I would say is, people have a lot of different reasons for getting into the field, right? Some people love the kind of the hype and the glamour associated with it, which is totally fine. I mean, I absolutely understand that. It is very exciting to be part of the field. But you have to make sure you're doing the things that are right for you, right? If you, it's as the field evolves, there are going to be roles that are more technical and roles that are more managerial or kind of less technical, right? And you have to begin to understand where you want to fall on that spectrum, right? And you kind of, just because someone hasn't done something before, or just because some company doesn't have the exact type of role that you want, don't be afraid to give something slightly new a try, but also keep your goals in the back of your head, right? Don't be afraid to be the first person to do something, right? That's going to be happening a lot in our field, right? People that are kind of charting their own path, right? And so, um, be open-minded, I would say, whether in research or not, whether you're working at a company or not, like, I think it's important to be in touch with the reasons that you're doing something, and to really to honor those reasons and who you are as a person. Um, and yeah, don't if you're not enjoying it, then that's okay, and you'll figure it out. And if you are enjoying it, that's great. But things are full of twists and turns, right? Like, I didn't know, am I going to work at a startup? Am I going to go straight to grad school? And now it's like, I don't know what I'll do after grad school. Maybe I'll do this or this or this. I don't necessarily think the certainty aspect. I don't necessarily think certainty gets narrowed down with time, or rather, I don't think that number of options gets narrowed down with time. It's more like, how confident are you in trying something at this point in your life? So just try to be kind of optimistic and happy about all that. That's what I would say.
Dr. Nishaad Khedkar, it was a ravishingly splendid and engaging conversation. Phenomenal. I just loved having this conversation with you. It was
I'm
lovely.
very glad. I'm very glad,
Thank
and
you
thank
so,
you
so
for having
much.
me on. Of course, this was wonderful. I'm really glad that people are interested, and I thought this is a really great platform for spreading knowledge. So I hope you continue to do this kind of thing for a very long time.
Definitely.